Welcome to Chem Crash. Today, in our first lesson of pre-organic chemistry, we're going to be talking about atomic orbitals. The first thing we need to understand when we're talking about atomic orbitals is that electrons are not just orbiting particles. What a lot of you guys might be used to seeing is something like this, where we have the nucleus in the middle and we have circles around it to represent where the electrons orbit. My circles are terrible. You draw in electrons like this, and what we get is a representation of how electrons move around the nucleus of an atom. This is actually an inaccurate representation. The reason for this is that scientists have discovered that electrons are not only particles, or do not only behave as particles, but they also behave as waves. So what that means is this representation of how an electron moves, which only depicts or considers an electron behaving as a particle, is inaccurate. The fact that an electron also behaves as a wave means that we need a different understanding of how an electron moves. So scientists such as Schrödinger created something called the wave equation. And the wave equation is something very complicated that you don't need to know for organic chemistry, at least this level that we're doing. Something very complicated that describes how an electron moves. And scientists such as Heisenberg came up with something called the uncertainty principle, which further describes the movement of electrons. And what we get as a result are atomic orbitals. Atomic orbitals describe the region in space. Describe the region in space. Actually, 3D space to be clearer, where the probability of finding an electron is very high. So very high can look something like 90 to 95%. So evidently a very high percentage. Atomic orbitals look something like this, where this circle or this sphere shows the region in space where electrons can be found. So electrons are very highly likely to be found in anywhere around this enclosed circle, this sphere. And electrons come in many different shapes and sizes. Sorry, not electrons. Orbitals can come in different shapes and sizes. This is a 2s orbital, this is a 2p orbital. So obviously they look very different. Now the little symbol that we have here in the middle of the orbital is called the wave function. So this represents the wave function. And the wave function is something that's complicated and is related to the wave equation, Schrödinger's wave equation. And it's not something, again, that you need to understand fully. But what you do need to note is that orbitals have different phases depending on the amplitude of the wave function. So phases are represented usually in different colors. You can see that this phase, which is represented with a negative wave function, and this phase, which is represented with a positive wave function, are represented in different colors. And that's how you're usually going to see them. So the positive and the negative here isn't the same as the positive and negative you usually see in like math or something. It doesn't necessarily mean like positive or negative, but they're just to show or represent different phases. So what the phases have to do with orbitals and why it's important for us to understand is that where two phases, or the boundary between different phases, are nodes. So right here is a very bad circle. Right here is the boundary between this positive wave function and this negative wave function. So that would be a node. And what a node is a region where the probability of finding an electron is 0, or the wave function is 0. So the probability of finding an electron can be represented by the wave function squared. So at a node, the wave function is 0, and the probability of finding an electron is also 0. So nodes can be circular like this, which we call a nodal surface, and the nodes can also be planar like this, which we call a nodal plane. So in these regions, we'll never find an electron there. And these regions are always where two different phases meet, so the boundary between the two phases. The most important types of orbitals that we're going to be discussing in organic chemistry are the s orbitals and the p orbitals. So the s orbital, as you can see, is very spherical, and it's symmetrically spherical, which means that no matter what orientation you consider it, it'll always be the same. There's not an orientation because it's a sphere. It's symmetrical everywhere. We also have the 2s orbital, which has this the nodal surface. We'll also be looking at a p orbital, which is not spherically symmetrical. It's more of a dumbbell shape, and you usually draw it like this, almost like an 8 or an infinity sign. And the p orbital has all p orbitals have a planar node. Now, the p orbitals, because they're not symmetrical, they're not spherically symmetrical, they can have different orientations, and because there are 3 dimensions, they can have 3 different orientations. They can either be aligned with the z-axis, the y-axis, or the x-axis, giving us the 2pz orbital, the 2py orbital, and the 2px orbital. So, sorry about that. We're going to be seeing the importance of these orbitals and their specific shapes in the next video, where we talk about their role in forming bonds, and you'll understand why these shapes and their behaviors are important. Thanks for watching.